All right, next I'd like to look at mid-latitude cyclones and how that relates to superstorms and also to the formation of tornadoes. And so oftentimes we look at kind of a classic textbook example of these mid-latitude cyclones as they occur in the middle U.S. And the reason why these tornadoes tend to, something like 80% of tornadoes happen in the middle of the U.S. We call it Tornado Alley. So I want to talk about why this happens and why the whole area is so conducive to the formation of these kind of mid-latitude cyclones. First of all, what we need to get this kind of thing going is a convergence of warm and cold air. And so we might wonder then, well, what is it about the middle of the United States that is so conducive to having cold air from the polar regions combine and essentially collide with warmer air that's coming up from closer to the equator? And the answer is you need a long, continuous landmass that doesn't have many mountains. And so we don't get this so much in the Rocky Mountains over here. Because the Rocky Mountains tend to funnel the motions of these airways into the path of least resistance, which tends to move along the lower elevation paths. And we also don't tend to get this kind of activity happening as much over water either, because water has a somewhat constant temperature because of its high specific heat capacity. And so that means that the differences between the hottest air and the coldest air over large surfaces of water are going to be much lower. But here in the United States, the middle part of the United States, this is the longest continuous mass of fairly low elevation land in which you can have very, very cold temperatures up in the polar regions because of the low specific heat of land in relationship to the very warm air which is moving up from the more tropical region. And also, not only do you need a convergence of warm and cold air, you also need, if you want to make these storms have a significant punch to them, you need to have water in the air. So you need a source of water. So in the United States, our source of water is typically the Gulf of Mexico. And this water is relatively warm, but with global climate change appearing to really be taking hold, there were some temperatures of the water that were associated with some hurricanes and cyclones that was between 85 and 90 degrees just this last year. So this is a source of water. It's not only a source of water, it's a source of warm water. So warm water is the best. So here you have this warm, moist airflow moving from hot to cold. And then you've got this colder polar air moving from cold to hot. And then in between the two, we have the boundary between the polar air and the warmer mid-latitude air, which is moving up. So what you tend to get here in this polar air are cold fronts, look like this, with the kind of jaggly looking teeth associated with it. So these cold fronts are going to be moving down from the north, and down here in these moisture regions, you're going to tend to get warm fronts moving up this way. And so these cold fronts and these warm fronts are in a head-on collision with each other in tornado alley. And the other thing, which tends to be the kicker here, is we have this region of low pressure, which is at the boundary between the Ferrel cell and the polar cell. And so the polar cell then has air that's coming in from the North Pole, which rises up here, and then the Ferrel cell has warmer air, which is moving up and then rises up in this region of low pressure from the warmer air mass that is associated with the Ferrel cell. So you have air that's moving up from the polar regions, air which is moving in toward this low and then up from the warm air regions, and so they'll have a tendency to mix then at this polar air boundary. And so this gives rise to what is called an occluded front. So when these two smash into each other, you get a stationary front, or an occluded front. And so this will happen in this region of low pressure air. And so basically then they're both beating heads with each other at this point, and become stationary. But this is a low pressure region, and there are going to be some places where the low pressure cold air pushing this way will have more of an effect, and there'll be other places where the warmer air from below associated with the warm front will get the upper hand. And so what this will tend to do then is create wave-like structures in this polar front. So it creates this wave-like or undulating pattern to the polar front. And so in this region then, a lot of times the cooler air may gain an advantage. And in this region, where it's pushing up, the warmer air gains an advantage. And because this whole thing is a low, a lot of times what will happen is that because the cold air moves faster than the warm air, it'll start to catch up. So typically it moves about twice as fast as the warm air front. And so what can happen then is that the cooler air start to move, spinning around the low toward this region of the warm air. And so this thing then is outrunning the high pressure warmer air, and the cold air front then is moving in like this. And so what we tend to get at this point then is a undercutting of the cold air with the warm moist air, which was already in this region. Remember, this was warmer air that's down here. So now the cool air is starting to get a little bit of an advantage. So it's starting to rotate around the low, and it's cutting into that warmer air, pushing it up to higher elevation. And so as the cold air undercuts the warm moist air, which is in this area, this is a warmer region behind the warm front, we can get a superstorm starting to form. And so this is then kind of the genesis of a mid-latitude cyclone. And as the cold air starts to cut into the warm air front along this boundary, we can get something that looks more like this. Sorry, this way. And along this whole boundary, it's already undercut the warm and created a huge, this is kind of like the eye of the storm. So this is a very big low in here, and so it's like the eye of the storm. And then the cold air is catching up with the warm air along this warm air front and creating these superstorms in that region. So it starts out like this, but then you get an undulatory pattern. And then that undulatory pattern is associated with a rotation in which the cold air moves faster than the warm air and starts to catch up with it, that can undercut this warmer, moister air and create superstorms, which are highly unstable regions of cumulonimbus clouds, but we could think of them as being all together in one spot. And so this is where you can get your very large mid-latitude cyclones. Now if we look up at the data projector, we see here on page 334 of your text that we have this occluded front here. This is at the surface, and then up high we also tend to have a low. Now, what does this low up here represent? Well, a lot of times the rising of warm air will be associated with a low pressure region that is at altitude. And so sometimes that can come from the jet stream. The jet stream, the polar jet, happens to be moving right over this region. Then that can help to draw air up and make your superstorm more potent. And so then the high pressure region then starts to catch up with the low pressure region. And then in this area where they overlap, this is essentially the eye of the storm, that everything is rotating around, and then the cold air is wrapping around this and creating the kind of a structure that we normally associate with a mid-latitude cyclone. And so here we see this circulation, here's the low, the center, and we see this circulation then of cold air and warm air that is tending to get this, this kind of a classic pattern for what the mid-latitude cyclone would look like. And so, in terms of the storms that can be produced by this, as the low, I'm sorry, the colder air undercuts the warmer air, this tends to push the warmer air very quickly to higher elevation. Okay? And so what we're seeing here from this airflow is that we have this warm moist air which is coming in, but then it's being undercut by the cold air that is associated with this cold front moving in. That tends to push the clouds up very rapidly and cause this warm, moist air to start to condense. And so this is when we start getting these very large downpours. So here's a picture here of unstable supercell kind of a cloud, like the one that we were just talking about. And then there has to be a flow downward, just as there is a flow upward. And so typically the flow upward tends to happen near the outside of the cloud, and then the flow downward can happen in the middle. And this can give rise to microbursts, where this air flows out. This is the outtake for the superstorm. And you can get these microbursts in which you've got very, very intense rain happening over a relatively short distance. Okay. And so this instability then can give rise to very strong storms and can also produce tornadoes. And so in order to get a tornado, what you need are what we call wind shear. So tornadoes are often found in these superstorms and come from the fact that you need two influences. That are necessary for a tornado. First thing we need is wind shear. Meaning that we need winds that are traveling in opposite directions at different elevations. And so typically then you may get the cold air being inserted from the cold air front here. And then at altitude you may have an outflow of warmer air. And so what this will tend to do then, if the conditions are right, is this wind shear between the differences in wind velocity at lower altitude, higher altitude, can then create these horizontal cylinders. Of rotating air. And so these things then would be rotating like that, but they would have a spatial extent to them that would be associated with this wind shear that is happening near the surface. So that's the first thing you need, is wind shear. That creates the horizontal cylinders. Of rotating air. Then the second thing you need is uplift. And this uplift can happen when cold air undercuts warm air. And does this rapidly. So the net result of this then is that the rapidly rising winds take the horizontal cylinders and turn them vertical. And then they can rise up toward the center of the superstorm. And so the superstorm then can generate this strong updraft from colder air undercutting warmer air. And then the warmer air, being less dense, tends to rise up quickly. So it could take these rotating cylinders along for the ride and lift them up from this horizontal orientation to this vertical orientation, and can then connect in with the lower pressure at altitude. So you need low pressure at altitude to enhance this uplift. And so if the polar jet stream is overhead at altitude, this is very helpful in forming tornadoes. As well as superstorms. So the superstorms, like the instability that is associated with the low pressure at altitude, causing these cumulus clouds to grow, expand, and cool, generate these huge rainstorms. But then you can oftentimes get, because of this very warm air that is moving in from the Gulf of Mexico, you can get the cold air undercutting that and forcing that up very rapidly. Then you have the moisture, and then you have essentially the perfect storm if you've got the lower pressure polar jet up here, which tends to then enhance and give more impetus to this updraft and give it enough power so that it can literally take those horizontal convection cylinders and turn them into vertical tornadoes. Okay, so here we can see part of this in action. We see the warmer air coming in, so we have an inflow of warmer air from below. You have the air from the cold front moving in this way. You have an outflow of air coming this way, and then you have the warmer air which is being brought in the vicinity of this tornado, be drawn up. And then up here, near the tropopause, you could have the jet stream, which helps to enhance that upward flow. And so what we're seeing then for the actual structure of these supercell cloud formations is something that is very dynamic and changes very, very quickly. And so here is a picture of a super cell storm, but from one moment to another it changes considerably in structure. And so what we see in terms of an actual structure at any given moment for the storm could be thought of as being, in a sense, some kind of average behavior, but not necessarily what you would always expect to see when you were looking at one of these